Hi, my name is Nick Oldham, and I am an undergraduate at Iowa State University. I'm here today to talk about the synthesis behind our NaPSiSON Glassy Electrolytes. These glassy electrolytes are used in batteries so that we can have a safer alternative to liquid electrolytes. Liquid electrolytes are effective, but they lack the safety and potential lifespan increases that a glass can have. Glasses can prevent dendrite formation, which can help prolong the lifespan of the battery and help it maintain its charge over a longer period of time. These glasses are also made of sodium instead of lithium, which means that they can be cheaper to source and easier to find on a grid-scale energy storage solution. These glasses have some unique design requirements, including high conductivity, which is not common in glasses, and a large working range. This glass system can be seen as 5 different components, of which 3 I'll be focusing on. These 3 are the most difficult to make, and so they have the most going on behind the scenes to source them. Starting with sodium sulfide, we'll then talk about silicon sulfide before finally touching on napon, which is a precursor glass for this system. Sodium sulfide is the simplest of the set. It is hydrophilic, but we can find it on the open market. Hydrophilic means that it reacts with any water that's in the atmosphere, so we have to buy it while it's stored under argon, then put it in our glove box where it's stored under nitrogen, and then directly before adding it to our glass system, before our glass melt, we have to calcine it or heat treat it to vaporize off any water vapor that might be in that sodium sulfide. Now talking about silicon sulfide we actually cannot find on the open market in the quality that we need, so we make it on our own in the lab. This is done using pure sodium and pure silicon, which we add to a etched out ampule inside the glove box. Then we bring it out of the glove box, evacuate the air out, and then seal it. Then once we have that sealed empty atmosphere, we then heat the entire ampule in a 2-day long heat treatment process. Then we bring it back out, bring it back into the glove box, break it in half, and harvest out the silicon sulfide. We do this to yield around 70 grams in each batch, and we have one batch ran every month or 2 in the lab, so we go through a lot of this material. We need that really high purity to maintain high quality glasses, and that high purity mostly comes from managing the amount of sulfur involved in the reaction. We start off with a very high sulfur content to make sure that all the silicon reacts, and then after this extended heating process, where we have this elevated, angled, spinning ampule that's heated up to 1,000 degrees Celsius. After that process, we then have to take the ampule out and reheat it again to distill off the sulfur and get it to run to the other end of the ampule. Once we've distilled off the sulfur, we can then have this ampule brought into the glove box and broken in half. This product is actually very solid and very hard, so in trying to work with it, you have to use a chisel and a hammer to try and get the exact quantity you need for the certain composition you want. It is unfortunately unstable in a specs mill, something where you have a steel ball mill, because the steel balls will actually separate the silicon away from the sulfur in the silicon sulfide bonds and ruin the purity of the sample. It's also hydrophilic, which means that we have to calcine it again right before adding it to our glass system. Now looking at napon is luckily easier to create in terms of its impurities, but it still has some difficulties. We start with NaPO3, which is easy to make in an oxygen atmosphere, and then we cast it into these bar shapes and then react it through ammonolysis, where we take our NaPO3, which has only oxygen, and then we replace some of that oxygen with nitrogen by flowing ammonia and nitrogen gas across the glass as the glass is sitting at an elevated temperature. And when you do this, you get these bubbles that form in the glass, and those bubbles are actually the water vapor escaping while the nitrogen is incorporated. We have varying amounts of nitrogen in each of these glasses, and it's hard to control that going in, but you can measure it afterwards and control how much napon you add to your glass system to control how much nitrogen you add to the glass overall. In the end, we combine all the different starting components together, do our final glass melt, and then collect it through either splat quenching or annealing into a variety of shapes, including discs for conductivity or plates for making batteries. Overlooking our entire series, you can see while it's complicated, there are methods to create any even glass in this system. Once we've made all of these glasses, we can then collect data from them using electrochemistry methods, thermal analysis methods, different methods of characterization, and also by making cells out of this glass. We've made cells that are actually running and generate current, and we can analyze how they perform in that environment. I'd like to thank everyone who's helped me in this project. in our continuing efforts to try and make battery science better. I'd also like to thank all of our funding sources for the amazing support they provide us.